Good morning, ma'am. I am B. Anil Kumar from CSC A section. My topic is minimum cost spanning tree. Introduction to minimum cost spanning tree. Minimum cost spanning tree are crucial in graph theory and network design. They connect all vertices in a graph with the minimum possible total edge weight. Understanding minimum cost spanning tree is essential for optimize the transportation, communication, and utility networks. Definition of spanning trees. A spanning tree is a subgraph that includes all vertices of the original graph. It must be connected and contain no cycles, ensuring a single path between any two vertices. The minimum cost spanning tree has the last total edges weight amount possible spanning trees. Properties of minimum cost spanning trees. Minimum cost spanning trees are unique if all edges weights are different. Otherwise, multiple minimum cost spanning trees must exist. They provide a framework for efficient network design, reducing costs and improving connectivity. The total weight of the minimum cost spanning tree is always less than or equal to the total weight of any other spanning trees. Application of minimum cost spanning trees. Minimum cost spanning trees are used in designing efficient road networks and telecommunication systems. They play a virtual role in covering algorithm within data analysis and machine learning. Other applications include circuit design and optimizing the layout of electrical grids. Algorithms for finding minimum cost spanning trees. Prism's algorithm, popular method that build the minimum cost spanning tree incrementally. Kruskal algorithm is another efficient approach that focus on the edges of the graph. Both algorithms ensure the creation of a spanning tree with the least total edge weights. Prism's algorithm explained. Prism algorithm start with a single vertex and growth the minimum cost spanning tree one edge at a time. It selects the smallest edge that connects a vertex in the tree to a vertex outside it. The algorithm continues until all vertices are included in the spanning tree. Kruskal's algorithm. Kruskal's algorithm sorts all edges by weight and adds them one by one to the minimum cost spanning tree. It only adds edges that do not form a cycle with the already included edges. The process continues until there are V1 edges in the spanning tree where V is the number of vertices. Comparison of Prism's and Kruskal algorithm. Prism's algorithm is better for dense graphs, while Kruskal's is more efficient for sparse graphs. The choice of the algorithm may depend on the specific structure of the graph and edge weights. Both algorithms produce valid minimum cost spanning tree but different their approach and efficiency. Graphs can be represented using adjacency matrix or adjacency lists. The representation affects the performance of algorithm used to find minimum cost spanning trees. Understanding this response representation is keys to implement the algorithm effectively. Edge weights and their impacts. Edge weights represented the cost, distance, or time associated with traveling an edge. Assigning appropriate weights is crucial for accurately determining the minimum cost spanning tree. Uniform weight may lead to multiple minimum costs, while varied weight of the cost personalized certain path. Running time of algorithms. The efficiency of finding an minimum cost spanning tree depends on the algorithms and data structure used. Prism's algorithm can run in O E log V time using priority queues. Kruskal's algorithm runs in O E log E times when using efficient sorting method. In network design, minimum costs minimize the total cost of laying cable or pipes. Buying using minimum cost spanning tree algorithms, engineers can ensure efficient resources allocation. Real life applications include telecommunications and water distribution systems. Real world example: transportation systems. Minimum cost spanning tree can optimize routes in transportation network, reducing travel time and costs. By analyzing various paths and their costs, planners can create efficient transmit systems. These applications can lead to significant saving in both time and resources. Challenges in finding minimum cost spanning tree. Finding the minimum cost spanning tree can be computationally intensive for large graphs. The accuracy of edge weight can significantly impact the resulting spanning tree. Graph structure and density can complicate the choice of the most efficient algorithms. Variant of minimum cost spanning trees. There are various minimum cost spanning tree variants, including bounded degree spanning tree and Steiner trees. The variants cater to specify constraints and requirement in network design. Understanding this variant expands the applicability of minimum cost spanning tree consists. Advanced topic in minimum cost spanning tree. Advanced Advanced topics include dynamic minimum cost spanning trees where edges can be added or removed dynamically. Research is ongoing into more efficient algorithm and heuristics for large scale problems. The study of minimum cost spanning trees intersects with the other fields like operations research and computer sciences. Futures directions in minimum cost research. The exploration of parallel algorithm for finding minimum cost spanning trees is a growth area of interest. Researchers are also looking into better handling of real time data for minimum cost applications. Future development may lead to more efficient tools for complex network optimization. Example Example problem: consider a graph with the following nodes and weights edges A to B weight 4, A to C 1, B to C 3, B to D 2, C2D 5, C2E 8, D2E 7. Solution with Kruskal's algorithm. Sort the edges by weight. Sort all edges in ascending order of their weights. A to C 1, B to D 2, B to C 3, A to B 4, C to D 5, D to E 7, and C to E 8. Start from the smallest edge. We add edges to the minimum MST as long as they don't form a cycle. A to C added to MST, and B to D added to MST, and B to C is also added to MST, and A to B is skipped because it would form a cycle. A to B, B to C. Fifth, C to D. C to D is also skipped as it would form a cycle. D to E added to MST. Total cost. The total cost of the minimum spanning tree is 1 plus 2 plus 3 plus 7 equals to 131 plus 2 plus 3 plus 7. Final MST. The minimum cost spanning tree include the edges A to C, B to D, B to C, D to E, and the total cost of the MST is 13. Conclusion. The minimum cost spanning tree are fundamental in optimizing various network designs, and understanding and applying minimum cost spanning tree algorithm can lead to significant cost reductions. As technology advances further, research will enhance the efficiency applicability of minimum cost spanning tree. Thank you.